Hey guys, so in this video, let's discuss Leetcode 1091. And this question is asked in Facebook, Amazon, Google, and Microsoft interviews in the past 2 years. So for this problem, we're gonna be given an n by n binary matrix, which means we have the same number of rows and the same number of columns. And for binary matrix, it means the matrix will only have value either 0 or 1. And we're gonna return the length of the shortest clear path in the matrix. If it doesn't exist, we return -1. So a clear path means we travel from the top left to the bottom right, and all the visited cells is 0, which means we can only move from 0 to 0. We cannot move to the cells with value of 1. And the adjacent cells are the 8 neighbors, which means top left and the bottom right and all the diagonals. So the keyword for this question is shortest. So usually for questions like to find the shortest path or minimum number of steps or anything like that, we use BFS. So for this problem, we're gonna use the same algorithm to solve it. So for every node, it will have 8 children, right? Like all the 8 directly connected nodes are its children. So we can translate the matrix into a graph where every node will have 8 children. And then we just use BFS to travel through all the neighbors layer by layer until we reach the destination. Then we can guarantee that we always get to the destination with a minimum number of layers, which means the shortest path. Like we use the minimum number of steps to reach there. Okay, so let's get started. So first of all, we need to consider edge cases. Like if the starting position or ending position has a value of 1, then of course we can reach there, right? So let's consider the edge case first. So n equals length of grid. And if grid 0, 0 exists, if is value of 1, or grid n minus 1, the n minus 1 is the bottom right is 1, then we return -1. Now we need to consider, for BFS, we need to use a DQ and a visited set to track the cells we have visited. So collections import DQ. All right. So visited nodes equal to a set, and then the Q will be DQ. Now we need to add the initial node, add the starting node into the queue, and also append the starting node into the queue. Okay, so for this one, we need to append a 1 as well. So for every, which means, let's make a comment there. For every item in the queue, it will be row, column, and the steps. So which means these steps means the number of steps we need to get there. So the starting node is like the first node, right? So that's we just get there with the first move. So the first move will be at the starting node. So we need to keep track of the steps which we're gonna return, like which will be the shortest steps we need to return. All right. So while queue exists, so row, column, steps equals q dot pop left. So we just pop it left. And if we reach the bottom right, then we're gonna just return it. Just return the steps. Otherwise, we're gonna just start the BFS algorithm. So for child in, okay, I need a helper function, get children. So child in get children, row and column. So let me just define a helper function, get children. So children, initialize the children. And we'll just return the children. So now we're gonna find the children to visit, which is all the 8 directly connected node cells. So for I, j in, let's see, 1, 2, 3, 4, 5, 6, 7, 8. Okay. So R plus 1, C plus 1, R plus 1, C, R plus 1, C minus 1. And R minus 1, C plus 1, R minus 1, C, R minus 1, C minus 1, R minus 1, plus 1. Okay. R and C minus 1, R and C plus 1. Yep. And if I is, of course, if it's within the range, and I is less than n, and j is within the range, then we just append it to children. Okay, so now let's get it. So RC, so for each child, right? So when we're gonna append the child to the queue, so if it's not visited, if child not in visited, and okay, so let me see, child row and child column. Row, child row, and the child column. Yeah. So if the child row and the child column not in visited, it's not in visited, and then the value, the grid value of that is not 1, and then not, it's 0, which means child R, child C, and the not, if it's not, then we can just append it to queue, right? First, we just add it to the visited. So this is visited, and then queue dot append. So we need to append the child and the steps. So this one here, we're gonna increment steps because we're moving to a new neighbor. So the steps will be incremented by 1. So now we are exhausting all the. So here in the while queue loop, we're exhausting all the all the children, right? Like if none of them reach the end state, then which means we cannot reach the bottom right, bottom left. So we just return -1. So let's see how it goes. All right, looks good. So time complexity wise, like we are basically visiting every node in the matrix, which will be n squared. And the space complexity wise, we are having a visited set and a queue, right? Which theoretically we can have all the nodes there. So which is n squared as well. All right. So this is the end of the video, and I'll see you guys in the next one.